Okay, so I think we can get started. So my name is John Horton, and I'm the moderator for our second plenary session. And people always say, the next two speakers need no introduction, and I think in this case, this is absolutely true. So Eric and Susan are going to be talking to us about, I think, two really interesting topics. And so the format here is Eric will go first. He'll talk for 15 minutes. We'll probably have time to maybe do one or two questions in between while Susan is getting set up. Then Susan will talk for 15 minutes. And then after that, it'll be open Q&A. And we'll, there's a little thing where you can ask questions. And so we'll pull out questions from that. And so without further ado, Eric, it's all yours.
Thanks, John. And it is so good to be able to join you all at Code. It's one of the highlights of my year every year. And I'm sad that I can't be at MIT for it, but I guess all of us are doing it virtually. And here's yet another record attendance. So anyway, looking forward to hear your questions and comments. What I'm going to talk about is a new way of measuring well-being in the economy using massive online choice experiments. So let me just share my slides here. And we call this GDP-B. The B stands for benefits. It's an alternative that can be used alongside traditional GDP. And really a key enabler of this has been the ability to do lots of online experiments, sometimes at massive scale, and allows us to measure free goods and new goods that are otherwise basically missed from the GDP statistics and therefore a lot of our discussion and well-being. Now, this is a problem that was understood right from the beginning when Simon Kuznets and his team invented GDP. He said, do not use GDP to measure the welfare of a nation. But of course, that's what everybody does routinely because it's kind of the only game in town. It is not a measure of well-being, it's a measure of production. And sometimes those are correlated, so that helps. Furthermore, most of our economic statistics are one way or another, or many of them are based on GDP. For instance, productivity is simply GDP divided by hours worked. So if you mismeasure the numerator, you mismeasure productivity by just as much. So let me just dive in a little background on what GDP versus consumer welfare. Some of you hopefully know this, but just as background. There's the green areas there are consumer surplus. The blue areas, the blue rectangles is price times quantity, what you spend on things, which is essentially what GDP measures. And the good thing is for a lot of goods and services, cars, haircuts, apples, if you get twice as many of them, you kind of get twice as much consumer surplus. So they're proportional. And that's why this convention of describing how well off we are, or how well a country is, or how things change from year to year by looking at changes in GDP isn't totally crazy. The problem is when you get to digital goods, things that cost zero, like free maps or Wikipedia, then you can get a big increase in consumer surplus, a lot more articles or downloads or views, and no real change in GDP. Maybe some changes in electricity, but it's not really notable. So you're missing the benefits that these goods are creating, and we all know that these goods are becoming more and more common. So there are two features we want to zoom in on to measure better. One is the free goods I just noted. The related issue is new goods. When something's introduced, there's a tremendous value just from the existence of the product that is not properly captured in GDP either. And again, these have been recognized problems, they just haven't been addressed. So our metric GDP-B for benefits seeks to measure that, seeks to measure not the spending or the production, but the consumer surplus or the benefits. And we're using these digital experiments to go after that in a way that really would have been difficult, if not impossible, previously. And I think you all know there's been an explosion of free goods, including this code seminar on Zoom that people have access to. And what's happened to GDP? Well, back in the early 80s, the section of the economy that accounted for all these digital goods, and for that matter, for software, books, music, magazines, was about 4.7% of GDP. And after this explosion, it went all the way up to 4.7% of GDP. So it's as if nothing really happened. And that's, as I said earlier, because it's not measured. It's not designed to be measured in the economy. And new goods, you see a similar problem. 20 years ago, there were about 80 billion photos taken worldwide, according to Hal Varian's work. 15 years later, it was 20 times more. But meanwhile, the price of photos the marginal cost went from about 50 cents to essentially zero. So what happened to GDP? Well, GDP doesn't count the number of photos. It tries to measure the money you spend on film, if you guys remember what that is, cameras and all the whole process. Furthermore, most photos now are shared, not sold, and you don't buy the components for them. So it's disappeared largely from GDP, and so it's even worse than not being counted. It's got the wrong sign as we get more benefit from these goods. And it's not just cameras. Here's a ad some of you may have seen from the early 1990s, and virtually every item on this, the alarm clock, the music player, the movie player, the video camera, are now bundled into our phones here. And a lot of new things that are maybe even more valuable, GPS and ebooks and fitness monitors. So there's a series of papers that we did this with in Brookings, in PNAS, in the AEA papers and proceedings, and Harvard Business Review. And as I think I mentioned earlier, it's joint work with Avi Collis, Erwin Dewart, Felix Eggers, and Kevin Fox that are working on this, and now a number of other people like JJ Yoon. So GDP-B, this new metric, develops a framework for measuring the welfare change. We have an explicit term for the new goods contribution that wasn't in traditional GDP, another set of terms for free goods. It ends up having like 4 times as many terms as the previous one, because you also have to have new free goods. And so that's worked out in these papers that I can refer you to for the theory. But let me focus on the empirical implementation here. We use a series of different kinds of experiments, online experiments. The main one that I'll be relying on is single binary discrete choice experiments. It's just a fancy way of saying, we give you 2 options and you have to choose between them. There's also something that's meant to be more incentive compatible called Becker-DeGroot Marshak lotteries or BDM lotteries. Best-worst scaling is something from the marketing literature. And we've just started using Bayesian truth serum that also seems to have some pretty good results that tries to get people to be more honest than they otherwise would be. In most of these things I'll show you, we do it with incentive compatibility. That is, we enforce people's choices, but we can do it at greater scale if we don't impose that requirement, and we can compare how accurate they are without that when we either impose it or don't impose it. So the first one I'll describe is a set of choice experiments we did at a lab at a university over in the Netherlands, where it was easy for us to enforce their choices and monitor what people were doing. We also did a much larger professional survey that is meant to be representative of the population. Typically, our experiments in those were in the tens of thousands of people. And then, as I mentioned, we've been able to scale it up to hundreds of thousands, or now millions of people. A really great platform that many of you may have been using is Google Consumer Surveys for that, where you can very cheaply do massive numbers of surveys. The basic SBDC experiment basically gives people a choice between keeping the good or giving up the good and getting some dollar amount in return. We vary that W, that dollar amount that we offer them. And then that allows us to scope out essentially a demand curve. When we offer more money, more people are willing to give it up. And then when we offer very little, most people don't give it up. So you can get kind of a downward sloping demand curve as we do that. Of course, there's going to be some noise and error in it, and some of the noise you can eliminate just by having larger sample sizes. We did some experiments to see how well that worked, and of course, as expected, you eliminate a lot of the idiosyncratic noise. Some of the noise may be biases that are built in, and the incentive compatibility is meant to eliminate that. But there are people who have, say, social desirability bias or other biases, and they'll tell you a number that is different from what they really mean, and that's why it's valuable to have these incentive compatible experiments as well. So let me describe one set of experiments we did to understand the value of Facebook. We've done this repeatedly for the past 4 years, so we can see what happens. And essentially, we offer different dollars amount for different periods of time and see what happens. For instance, we ask them to give it up for a month and offer them $50. And some people say yes, some people say no. You can think yourself whether you'd say yes or no to that. Other people we offer $5 or $10. Some people we offer it for a week or several months. And we enforce it for some of them and say, look, if we're going to monitor you, and if you say we're going to keep Facebook, fine, just keep it and you're done. If you say you're going to give it up in exchange for the money, then we monitor them. And as you may know, you can look at your friends on Facebook and see what last time they logged in. And we tell them if they haven't logged in for a month, then they'll get the payment. And so that's a way of enforcing it. For different goods and services, we have to come up with different ways of enforcing it. But that worked pretty well for Facebook. So what do we see? It did look a bit like a downward sloping demand curve. When we first did this back in 2016, you could see the slope. And then 2017, it changed a little bit. And interestingly, over time, the median value has been falling a bit. At first, it wasn't statistically significant, but now it's clearly statistically significant. And we're just finishing up one for 2020. It appears that the median user has less and less value for Facebook over time. We can also get a sense of the heterogeneity in the valuations. Not surprisingly, people who spend more time on Facebook tend to have higher values, and people with more friends or post more frequently or watch more videos, all those metrics. Women on average tend to have higher values than men. Older people have higher values. I wasn't quite sure why that would be the case, but I think it leads to the seventh item there, that the older people seem to be less familiar with Instagram or YouTube or other things that I don't know the name of that are substitutes, and therefore maybe have a higher value for Facebook as opposed to the near substitutes or partial substitutes. And I should mention, since we did this, a number of other people have replicated it. There's a paper by Cass Sunstein, Hunt Alcott, and Matt Jenskow et al. Have written a paper that came out in the American Economic Review that got very similar results to these numbers. So we sort of feel like there's some increasing credibility that these are about the right estimates. We also can do it for non-digital goods. It's a little trickier. We have to be creative. We've tried to estimate the value of cameras on smartphones. You know, they all have these cameras that are really valuable. And so we put this tape that can't be removed without being detected, safety tape, and paid people if it hadn't been removed for 1 month or different times. The numbers were staggering. This is a group of students in the Netherlands that we estimated, and we had to pay them about 60 to 70 euros in order to get them to agree to go without a camera for a month, which is remarkable when you think that the cost of manufacturing the smartphone cameras is about $20 to $30. So there's a huge value that they're putting on it. And by itself, this access to these cameras would imply a significant contribution to the benefits of GDP over time. So to summarize some of the key findings there, we have valuations that are consistent across the different ways of measuring it, whether it's SBDC, BDM, best worst scaling. When we do the incentive compatibles, I didn't quite show this, but they tend to be higher. The valuations tend to be somewhat higher when we enforce incentive compatibility, at least for most of the goods we looked at. I'll show you in a minute the ranking of the different valuations of different types of goods. Overall, Facebook worked out to be about $450 a year. And here's a little bit about how we did it with Google consumer surveys to scale it up to more things. So sometimes when you look at content, you have to do a short survey, and those are the kinds of surveys we did for millions of people now. And here are the valuations for Wikipedia, for email, search, video. As you can see, you get fairly consistent sort of downward sloping demand curves. The cutoffs are different. Of course, people have different valuations for these different kinds of goods. Music, not so much. Email and search, quite a bit more. Thousands of dollars actually in the cases of those. You can also do it for non-digital goods. Breakfast cereal has an implied consumer surplus of about $15 billion a year. That's an homage to Jerry Hausman and others who have measured consumer surplus in other ways and got similar estimates. Here's a chart where we looked at a whole bunch of different kinds of goods and services from indoor plumbing. Bob Gordon suggested that was the most important invention, and I think we have some evidence that he was right. Access to internet and personal computers also ranked very high. I was surprised that breakfast cereal is a little low, but I was surprised airline travel is even less than that. So I guess I may be one of the people who travels more than the average American by airlines. We haven't redone that in the age of COVID. It'd be interesting to see how that number changes. So finally, let me just say that this is meant to be a complement to the other metrics of the economy. The traditional macroeconomic indicators, they're in the bottom right, like GDP and productivity. They have the advantage to be quite precise, 6, 7, 8 significant digits. We look at how they change from month to month or quarter to quarter. At the other end of the spectrum, well-being metrics, there are a number of people who've looked at happiness or life satisfaction, sometimes asking a sample of people in a country how happy they are on a scale of 1 to 10. And maybe that's more important than GDP, but it's hard to be very precise about it. GDP is meant to sort of fit in between, more precision, maybe not quite as much as GDP, but also capturing something closer to well-being, the value you get, particularly in consumer surplus, and filling in that space of understanding how we're getting value from different kinds of goods. So if you want to, let me just, the final points are that GDP is still a de facto metric, but consumer surplus, as I think most economists would agree, is a better metric of well-being. By the way, we could also measure producer surplus, but that hasn't changed nearly as much. And Bill Nordhaus suggests that about 95% of the benefits of new goods comes in the form of consumer surplus, not producer surplus. But that would be a way of extending this slightly. These massive online choice experiments is really what's enabled this approach and allow us to plug the numbers into the equations for GDP-B. And it works not just when goods have positive price, but also when they have zero price, which is something that's missing from traditional GDP. And so this new metric, GDP-B, is one that we're fleshing out, and we expect to expand to a lot more goods and services going forward. So with that, I'm just about exactly on time. You can read the underlying papers on my website, also the new Digital Economy Lab website at digitaleconomics.stanford.edu. Feel free to click there and read more about them. Thanks very much.
Great, thanks so much, Eric. So we have a few questions while Susan gets up, and I'll just kind of paraphrase them a little bit. So we have one question from Sudeep Paul, who's essentially asking, what kind of traction can you get just by looking at, say, the price of ads for ad-supported free goods? Does that give you much traction?
That's a great question, and that was a couple of slides that I cut to save time, but I'm glad that the question got asked. A lot of these free goods are advertising supported, obviously Facebook, Google, etc. And there are three concerns with that. First off, technically advertising is not part of GDP, it's an intermediate good. So, in theory, it just kind of washes from one part to the other. Also, advertising revenues have been actually surprisingly flat, so it doesn't really show any change any more than GDP. But the most important reason that we don't rely on advertising as a metric is that the value that an advertiser pays or is willing to pay for an ad is very loosely correlated to the value that a consumer gets. You may read a Forrester report or some in-depth analysis that could be worth hundreds or thousands of dollars to you or to a company, and the advertising revenue that might be very small. Other things might have a very broad audience that people are sort of indifferent to, and that might, have a very, imply very large advertising value. So Michael Spence and Owen did a paper over 40 years ago showing that advertising and consumer valuations are not particularly well correlated. So it's not a good idea to just pop that in as a proxy.
And let me just, one more question. This is coming from Patrick, and again, I'm paraphrasing, but would you kind of use these lab studies or sort of a recruited sample? You have this worry that those may not be representative of people, so that a young person might care a lot about TikTok or something, and maybe an older person would care less. And so, do you have thoughts on kind of this generalization step?
Well, that's why we tried to do it from multiple different ways. And my first idea was really to focus mostly on the Google consumer surveys, because you get a very broad, pretty representative audience, although needless to say, there are people who are online, so you lose the people who aren't online, which are some. But it was hard to do incentive compatibility with those. So we're doing it all these different, I flashed through it pretty quickly, but many different kinds of samples, so you can compare the results from one to the other, for that matter, in different countries. Like one small surprising thing, when we did the survey, most of the valuations of Facebook, Twitter, WhatsApp, of most things were sort of similar in the Netherlands and the United States. One that was radically different was WhatsApp. Like WhatsApp was worth like 20 times more in the Netherlands. And I thought that was an error. And I said, you guys need to go back. We need to ask these questions again. And then we interviewed the people, and it turned out that, maybe as your questioner was saying, this population that we were checking from, just their lives depended on WhatsApp. They would not have any dates on Fridays if they weren't on WhatsApp. They wouldn't be able to hire a babysitter or be hired as a babysitter. They wouldn't get their assignments from their professor. So it was a really central part of their lives in a way it isn't for most Americans. Ultimately, I think that's kind of a feature, not a bug, that we can fairly cheaply kind of sample different populations and different groups and compare the numbers. And this heterogeneity in valuations, even within a group, different people have different values for Facebook. When you look at market prices, it's fairly rare that you get multiple different prices for different groups. It tends to be a clearing price, at least in the simplest kinds of markets. And with our approach, you can get something closer to the whole demand curve and see how it varies across populations. It makes it more complicated to think what is the true right number, and the answer is that there is no one right number. It depends on which group you're looking at.
That's nice. Yeah, it's kind of this collage of evidence idea. Okay, great. Well, we're going to have more time at the end. I know we have more questions. So right now I'm going to transition over to Susan.
Hi, can you hear me okay?
Yep.
Great. Okay. And it looks, is my screen all up?
Yep.
Very good. All right. Just always like to make sure before you go off to the races. So thanks so much for having me here. And I'm also, of course, a huge fan of this conference. It's one of my favorite conferences of the year, and I'm really delighted to be back. I was telling the organizers, they always put a lot of pressure on me because I have to come up with something new every time I'm coming to talk. And so this year I wanted to talk about a line of research I've actually been working on for several years, but it's a little bit off the sort of track that I've been talking about here in the past, where I've been working on machine learning and causal inference techniques from a more standard sort of treatment effect setting where, there is a treatment and a control, or maybe there are multiple arms of treatment. And we're trying to see whether they work, how much they work, for whom do they work. Today, I want to talk about a different strand of work, putting together machine learning and causal inference. And this is more around consumer choice. And so it's closer to the literature in structural IO in economics and the literature in marketing. But some of the questions and themes you'll see will be similar, both in attention to thinking about when you take machine learning into causal inference, you have to put a lot of attention into how you're training your models, what the objective is, and how you're validating the models. And so those themes will come in today as well. And then a second theme will be personalization. And so I've listed out my many co-authors. We have a couple of papers, and you can check out my website to see the different papers in this line. So just for those of you who aren't classically trained or IO economists, let me just sort of review the way that in economics and marketing, we often study discrete choices of consumers among products. So there's sort of a framework where you say, I can take the utility for user U, for product I at time T, and I'm going to decompose it into two parts. Now, at first, it looks like there's no point in the decomposition because both of the components have indices, but I'm going to put a functional form on one of them. And this error, this epsilon UIT, is going to be sort of the idiosyncratic shock that would just be some special thing that makes that's independent over time and across users and items that makes you buy a certain product today. And so the insight from Dan McFadden in the early 1970s, for which he won a Nobel Prize, was that if those errors have a particular functional form, if they're type 1 extreme value or gumbel, and you assume that consumers make choices to maximize utility, then the probability that the consumer U at time T makes choice I can be represented with this nice little functional form, which is e to the mean utility divided by the sum of e to the mean utilities of all of the items. And that's also, you'll recognize, as a functional form for a multinomial Logit model. And so it's basically saying that we can, if you estimate, another way to look at it is if you estimate a multinomial Logit choice model and you estimate the means for each of the choices, those can be interpreted as the mean utilities of utility maximizing consumers. And why does that matter? Well, from a prediction perspective, the interpretation doesn't necessarily matter, but from a counterfactual perspective, it does matter. If we want to think about what would happen if I change something, then I could change anything about this problem. I could add a product, I could take a product away, I could change a price, I could make it go out of stock. And this model, given that it's assuming consumers maximize utility, would tell us counterfactually what would happen. And it would also tell us how welfare changes. So these kinds of models are used a lot in like merger analysis, or welfare analysis of the type that Erik was just talking about, when you want to understand what happens to people's utility if two firms merge or prices change. And so down here at the bottom is the functional form that we often would put on a mean utility. This is actually a more flexible one than it's on the flexible end of what people have typically used in IO. We're going to have a price for item I at time t. This coefficient, delta U, is going to be a consumer-specific preference for price. And then there's going to be a mean utility that we're going to say user U has their own special utility for item I. And usually, actually, we'll model that even more, put more functional form assumptions on it to restrict it further, because it's going to be hard to estimate those. Now, as I mentioned, we use these models. What we do is we estimate some form of multinomial logits. We estimate parameters. We might, let them be. We might try to estimate the parameters directly, or we might allow them to have a distribution through like a random effects types of models. And then we do counterfactuals. And the cool thing about this, again, is that it's going to tell you if the price of one product goes up, how does consumer demand get redistributed among other products? And by the way, I should say this is in a category, so we can think of this as like we're going to have different, brands of potato chips, and we're going to, if the price of one brand of potato chip goes up, you're going to buy different potato chips. Now, when you go to the supermarket, there may be lots of categories in the store. Typically in economics and marketing, we focused on just one category at the time. And so one of the things my work is doing is it's using machine learning to try to look at lots of categories in parallel. So before I get to that, this is a group that thinks a lot about causal inference and making sure that we actually identify causal effects of something. And so that's actually a bit of a challenge when prices might change in response to demand changes. And so in the types of data that I'm going to be looking at, we're going to follow consumers over time, and we're going to see lots and lots of consumers making individual choices. And so the unconfoundedness assumption in this setting essentially would boil down to conditional on some observables that prices are independent or as good as randomly assigned relative to an individual's idiosyncratic error. And so the way you might interpret that is some things we're going to control for might be the purchases of other consumers in a given week, or whether it's a holiday or what day of the week it is. And so the idea is going to be that conditional on those characteristics, the price is as good as random. Or alternatively, you can think that whether a consumer shows up at the store on Tuesday or Wednesday is as good as random. And so in one of our data sets, the prices change at midnight every Tuesday night. And so essentially, and it turns out that that's kind of intentional, that Tuesdays and Wednesdays are basically very similar days in terms of grocery shopping patterns. And in one of the papers, we only look at data from Tuesday and Wednesday. And so you can basically think that, whether you came on Tuesday or Wednesday is like the experiment. Okay. And we're going to control for Tuesday and Wednesday effects, but it turns out those effects are not important. So, but we still want to assess whether this strategy is actually valid. It could be wrong, for example, if, and we're going to use, week effects basically, so that we're going to control for the week of the year as well. You could worry though that if a product is getting more popular over time and its price is going up over time, that even week fixed effects don't pick things up properly. There could be sort of an upward trend that's not captured there. And so generally Wednesdays are looking better than Tuesdays overall. So in order to do that, we do what's called a placebo test. And so in this, there's lots of different versions of placebo tests, but here what we do is we create a fake price series and we try to estimate whether we find whether we actually find falsely treatment effects of a fake price series. And so because what we're worried about here are unobserved time trends that are sort of gradual over time, the way we do this is we take the price series that we observe in the data, like this is a price series for organics fat-free milk, and we create a fake series by shifting that price series over. And then we rerun our models as with those shifted price series. And so this is a way of we assess our assumptions here with called the supplementary analysis. Again, unconfoundedness is not testable, but this is analysis that is supposed to convince you that our analysis is more credible. And so what you know is if you have null effects and you test a whole bunch of hypotheses, the distribution of your p-values should be uniformly distributed because sometimes you'll get big effects, sometimes you'll get small effects, and overall the p-values should be uniform. So what we see in all of the cases where we tried different versions of shifting price series, we see that our p-values, the cumulative distribution of p-values lies approximately on the 45-degree line, which is the uniform cumulative distribution. This red curve is the cumulative distribution of p-values from the real time series, and this is looking across different categories or different products. And what we see is that we generally see very low p-values, that is strongly significant effects of changing prices when we have the real-time price series, but not otherwise. So, encouraged by that, we then go off to the races with this model and try to estimate price coefficients. But as I'm still not going to be satisfied completely. This is sort of a first analysis. I'm now going to show you in a few minutes other ways that we try to validate our model. But first, let me tell you a little bit more about the model. Again, in traditional economics and marketing, you might write your PhD thesis about demand for paper towels or demand for yogurt. You typically have a small number of latent parameters, like you might allow there to be an individual specific price coefficient, maybe one for product quality. And you generally assume that items are substitutes within a category and you just ignore all their categories. So you might have a really big data set with thousands of products, but you just focus on like 5. And why is that? Well, that was because traditionally we would estimate these things either with maximum likelihood or often with Bayesian techniques. And people might take 3 or 4 weeks for their Markov chain Monte Carlo to converge. And so they were kind of limited in the complexity of the models. But modern computational techniques from machine learning have relaxed a lot of those constraints. And one of the things I've done with my computer science co-authors is try to adapt some modern techniques and specialize them to have good computational properties for this specific class of models. So what we're going to do is study many categories in parallel. We're going to still assume that, whether you buy paper towels doesn't affect whether you buy toilet paper. That doesn't affect whether you buy apples, but if you buy one type of apple, you're less likely to buy the other type of apple. And we actually throw away categories in these papers where that's not true. We have another paper that actually estimates complementarity between taco shells and tacos. I'm not going to talk about that paper today. It has a lot of interesting computational issues, though. So instead, in the papers I'm showing you today, we're going to use a version of the nested logit, which was introduced by Dan McFadden. And that model is basically going to allow you to have a shock to whether you buy a product at all, as well as shocks to the individual products. But it's basically going to allow whether you buy one kind of apple to be correlated with it, whether you want another type of apple. And that's going to be really important to fit the data because most people don't buy most products when they go to the supermarket. And treating that all as independent gives you bad results. And that's something that's been well studied in the economics literature. And then the other thing we're going to do is either use matrix factorization or neural networks to estimate the user item preference parameters. And that's going to allow us to share information. So if you like organic tomatoes, I'm going to learn that you also might like organic lettuce. And I'm going to share information across products, which is going to be more efficient. So that's the wrinkle or the new thing that is a natural thing to do for machine learning, but that people hadn't been doing in economics. So this is just a setup of the model. I won't go through all the gory details. It's just to kind of give you a sense of what it's all about. But the nested logit, it has a top nest where you decide yes or no whether you buy the category, and then a second nest where you choose what product to buy. And Dan McFadden's work showed how if you're maximizing utility, you can relate the parameters that you estimate in the sub part of the model where you choose which product conditional on purchasing to you put those together in something called the inclusive value, and then that term enters the part where you decide whether you buy or not. And so for computational reasons, we actually do this as a 2-step estimation, even though ideally it would be efficient to estimate them jointly. Interestingly, like back in the early 70s, they also had computational constraints, but for much smaller data sets and much simpler models. And so they did this in a 2-step way. Then we all learned to do it together, with small data sets and on our PCs. And now we've gone back to working on clusters and breaking it apart again because we have computational problems with much larger data sets and much larger problems. So I won't go into the computational approaches, but I'll just say we use variational Bayes, and we use a lot of tricks and tips to make this computation work quickly so that we can estimate the models in a couple of hours or even an hour rather than days or weeks. And it used to be days or weeks for much smaller models. One of the things that we emphasize in the paper is that we want, when we tune the model, when we choose how many latent variables and how rich the model should be, we want to focus on counterfactuals rather than just prediction. And so it turns out that it doesn't make a huge difference, but it makes some difference. And so the model specification you would use if you're really trying to do a good job estimating the effect of price changes is different than what you do otherwise. But our models do actually better than competing models, no matter how you test them. What we do to compare is we compare our model of jointly estimating across all categories with category by category models, where we estimate, in this case, 130 different nested logits, one separate for each category. The 130 different models actually has a lot more parameters, but it doesn't share information across. And so what we see is that using less parameters and sharing information across works better and works better both for prediction, straight prediction, as well as for seeing what happens on weeks where there's price changes or when things go out of stock. Now, as I mentioned, especially for my econ and marketing crowd, we're used to really thinking about the world that there's like a one true model, and we've consistently estimated the parameters, and we have a theorem that says that, like, we've converged to that one true parameter. Well, the machine learning way of thinking about it is more that where we're going to do a bias variance trade-off, and it's an approximation, and it's always going to be an approximation, and so we never really believe we've gotten the answer right. And so instead of relying on sort of a theorem that says that, oh, I've consistently estimated this parameter, instead, I want to find other ways to validate the model. But where I know that for some users, I may not have enough data to actually understand their personal price sensitivities. So one of the things that we do that's nice about these data sets with lots of price changes is it's like we have lots of experiments. We have thousands of experiments. So we estimate the model and learn about your responses to price changes from some of the experiments, and we hold out other experiments, and we can see how well we predict what happens in those held out experiments. So here what we did is we take every week and product with a price change, and we then for every, we held out shopping trips for consumers, and then we look and say, here's a week with a price change for a particular product. For that product, we put each consumer into one of three buckets: low price sensitivity, medium high price sensitivity, or high price sensitivity for that product. And that's based on our estimates from our model from the training data. But in the test data, we've just assigned them to buckets. And then what this picture shows is what actually happens in that held out test data. So everything in this picture is in held out test data, except for the assignment of the people to the categories, which was based on different shopping trips. And what we see is the people that we assign to be least elastic, the least price sensitive, don't respond much when prices change. And I've got the price changes on the y-axis because that's what economists do. So the price, but the price is the thing that changed in the data, and then we're estimating the demand changes. But I've plotted them the way that economists plot them. So the confidence intervals are these bars. And so what we see is that we've successfully distinguished the people who are very price sensitive, so that when the price changed in the test set, those groups did respond to price changes versus the ones who didn't. And so one of the themes here in general is that if you're trying to assess personalization, my model says, hey, you individual, you have a stamp on your forehead. I think that you should be low price sensitivity. But of course, we're only going to see the person with one price or the other. But a way to assess those types of models is that you can use your model to put people into groups. Now I have a group of people, and I can take averages. So what I'm really plotting here is there's a group of people. Some of them showed up on Tuesday, some showed up on Wednesday. The price was different on Tuesday and Wednesday. And so what I'm comparing is the average purchase rate from Tuesday to Wednesday. So I'm still comparing across people, but I use my model of individual sensitivities to put them into buckets. So once I've assigned them to buckets, I can take averages, and I can use my test set to assess my counterfactual model, even though I never observe for any individual their personalized treatment effect. So now let me show some things you can do with this kind of model. One of the things I can do is try to assess the counterfactual benefit of targeting and price and giving people different prices. So here I take two of the most popular prices in the data set, and up here is like a timeline. These prices might have fluctuated over time, and this is not that uncommon in supermarket data where prices fluctuate between two different prices. Then I can see the trips. These users showed up on different dates, and I've got a blue block if they showed up on a low price day and a red block when they showed up on a high price day. I use my model, where my model actually estimated for each person a price sensitivity, and using that model, I can optimally assign some people to get a coupon. So these L people at the bottom, users 5 and 6, I'm counterfactually saying, I think those people should get a coupon. Then if I want to see how good did my model do, I actually have this data. I saw all these people go to the store. If this is held out test data, I can say, well, my model says that I wish that I had assigned all of the users 1 through 4 the high price. I wish I had assigned users 5 and 6 the low price. But in practice, in the observed data, they got a mix. And so I can basically estimate, using observational study techniques, I can estimate the treatment effect of having gotten the high price versus the low price for my orange group. And I can also estimate the treatment effect in the test data for having gotten the high price versus low price for my green group. And using those, I can assess in test data whether my coupon strategy looks like it worked. And so in this particular case, I kind of got lucky. It looks like actually, I was expecting attenuated effects, but actually it turned out in this particular case in the test set, I actually found stronger benefits from targeting than my model suggested, although I think that's kind of a fluke. We also do things like try to test whether using individualized pricing versus demographic-based couponing would work. And it looks to us like the personalized pricing works better. Finally, something that's in progress, I've actually been working on this for like the last year, and we still haven't got our final results. We've been trying to look at using a different data set, a big data set from India. What happens, what's the value of additional data for targeting? And so we look at 3 kinds of data: retaining data longer for users, adding more different categories to the data set and allowing us to learn across more different categories, and adding more users to the data set. And we also look at the benefit from adding more data versus retuning the model and getting a richer model that better exploits the larger data set. And so we see, first of all, the value of data is highest for adding more days per user. That is, getting a deeper look at each individual user adds more value than getting more users or adding more categories. But we also see that holding the model fixed, you get moderate improvement in the quality of the model. But when you retune the model to take advantage of the full richness of a larger data set, you get a bigger boost. So these are preliminary results, so they could change. This is a very computationally intensive exercise that we're doing because we're resimulating and rerunning this model, hundreds of times with lots of different data sets and retuning and all of this stuff. So it's been a challenge to do the engineering to make this run fast enough to do our full set of simulations, but hopefully we'll have more complete results soon. And just to conclude then, we think in this environment of consumer choice, we can combine machine learning, causal inference with structural models. We can do counterfactuals. And even when we're looking at personalization, we can use tricks to try to figure out how to assess in held out test data the quality of our counterfactual predictions. Once we believe them, we can do things like ask about the value of data, which matters for privacy policy, merge policy, and antitrust policy. So I'll stop there. Thanks.
Great. Thanks so much, Susan. That was wonderful. And so now we have time for just questions more generally. And probably what I'll do is prioritize questions for Susan while it's fresh, but then we can kind of talk about things more generally. And while we're, so please use the Q&A chat to ask your questions. And so I'll start while use my moderator privilege here. One thing I was thinking about is just the fact that, the typical recommender system that does the kind of like people who bought X bought Y and kind of reflect that back to users, with the approach that you have, you could potentially do something that's more like sort of like price aware kind of recommender systems. And, maybe in a conventional grocery store that's a little hard to pull off. But if, more people are kind of buying their groceries online, you could use a lot of those same kind of that same playbook of Amazon, but do it in kind of a savvier way.
That's right. So in a short talk, I didn't get a chance to kind of give all the big picture. So thanks so much for asking that question. So I think that, things are changing quickly. So what I would say 5 years ago when I started on this agenda is already kind of different from state of the art now. But as of 5 years ago, I was not aware of large e-commerce organizations using price-aware recommendation systems. And I think a lot of that had to do with computational constraints. So it's very easy for, for something like Netflix or, name your favorite e-commerce firm to say, let's aggregate our data from the year. That's a manageable data set size. I mean, it's still big, right? I might have millions of users and thousands or millions of products, but then I have a big matrix and I can use matrix factorization to do recommendations. And that would be the state of the art. But of course, we know that behind the scenes, the data generating process behind that could be quite informative as to why people made the choices they did. After all, if Netflix never showed you this movie existed, you can't really infer much from the fact that you didn't pick it. If Amazon always ranked this product at the bottom of the page, or it was always at a high price, of course, it's not that surprising that you didn't pick it. So understanding what the user saw and what was presented to them is important. Now, in search engines, actually, we did keep track of the page views. So for a search engine, the way that those models are estimated to say, this is what was on the page, these were the ads you saw, these were the algorithmic results you saw, and we're going to think about how you chose from those. And that was part of the equation. But once you have more things changing, like prices and coupons and pictures and presentations, it gets really hard. And frankly, it takes a massive amount of infrastructure, and you're pretty limited on the models you can estimate once you try to keep track of everything that the consumer saw as they saw it. And I think a lot of social networks don't even keep track of the page views, right? I mean, they don't store, imagine like every person out there scrolling through their screens, they don't keep track of exactly what you saw when. It's sort of too much. So I think that it's not that nobody thought that this was an interesting idea, but I think, but neither in marketing nor in recommender systems, but there was a question of computational constraints and the ability to come up with a unified model. And well, is there an advantage of that model? So I think of our project as sort of trying to put those two things together to be like a context-aware recommendation system. But when you become context aware and you realize that you're choosing from a menu and you have substitution effects, things become nonlinear. So suddenly you have latent parameters in the denominator, which it turns out is harder. So these, that's part of where my brilliant computer science colleagues came in with some good computational tricks to try to make this work better.
Great. And another kind of related question, or I'll just summarize it. There's a question about just sort of when does more data about an individual consumer sort of stop mattering, or sort of do you kind of start losing any advantage to keeping that?
Yeah, so this is a really interesting question, and I want to emphasize that something that's kind of frustrating in general conversations about data, and especially in the policy domain, is that people are like, oh, more data is either people say more data is really important, or they say, oh, there's plenty of data, you don't need any more data. And of course, this whole conversation is vacuous without saying what kind of data, and for some data, there may be diminishing returns, and for other data, there may not be. So actually, even in comparison between US supermarket data and the Indian supermarket data, in the US, people come to the store less often and they buy bigger shopping carts. Well, in India, they go more often and they have smaller shopping carts. And so it actually becomes harder to kind of really learn about the person in the Indian data than it is in the US data. So in general, what kind of data matters more and when you hit diminishing returns is very context specific. It matters really what the underlying data generating process is and how rich it is. Like if you're well described by one parameter, then I don't need that many observations to estimate that parameter. But if your preferences over the 5,000 products in the supermarket are complex, then I need to watch you for a while to learn those. And even like in these settings where I'm seeing all your shopping over like 2 years, you still don't buy lettuce that often. You don't buy paper towels that often, and I might only see you buy paper towels at 3 different prices over the course of 2 years. So in this kind of data, you're still not that far down the learning curve after watching someone for a while. And so that's, I think, why there's, in this particular context, a lot of value to retaining user data for a longer period of time. Now, if you had a lot of closely related products, so if lettuce and if it's mostly like produce and there's lettuce and tomatoes and onions and everything else, then adding more similar categories might be really helpful, because once I've seen what you like about peppers and lettuce and tomatoes, I might know a lot about whether you're going to buy organic onions. So, you might not need more categories to help you understand preferences. And again, I just want to emphasize that how much data value is, it's really going to be context dependent, which is why I wanted to do an empirical paper and show that. But one other type of mistake people make in thinking about this is they imagine, especially if you're a classical economist, you imagine, oh, I have a model with 5 parameters. As I get more data, the precision of those parameters is going to go down with the square root of n. So if I have 500 million observations versus 1 billion, doesn't really matter. I've got the same parameters. But if you're actually trying to personalize things to people, like John, there's nobody just like you. There's nobody just like Erik. So, I might need 1 billion people to have someone who's, kind of similar to Erik and all of his quirks. And so actually, like, it really helps to have 1 billion people, because then I can find people who are closer to him to learn from and make predictions about him. So in that sense, as your models get richer and richer, as you get more data, you can get richer and richer models, which allow you to personalize more. And so I was expecting that to come out, and I knew that from my industry experience, but it really popped out big in the estimates I've done so far, that, getting more data, and if you keep the model the same, the real benefit of more data is you get richer personalization.
Thank you. And one thing I want to, we have a bit more time, and so I want to kind of open it up, more broadly if people have more questions for Erik, or if Erik has thoughts that he wants to weigh in, or we have things we want to discuss. I could also bring some more questions out of the
well,
chat.
actually, one quick thing that occurred to me as Susan was presenting it is some of the synergies between what she's doing and I'm doing. One of the difficulties we have is that when we do these massive online choice experiments for something like Facebook, it's easy to get lots of people who use Facebook. But for some of the more obscure goods, as we start going down the long tail, most people just have a 0. And it might be interesting to find a way to do some kind of hybrid work where we look at their actual revealed choices and then go further to try to estimate the valuations on top of that, rather than just a random sample of the population.
And so can I take a question from the Q&A?
Yes, you can see the Q&A questions as well, right?
Yeah, absolutely. Yeah, I wanted to mention, so I guess in my last answer, in case I wasn't completely clear, there are diminishing returns to data, absolutely. Although it can be actually like a little bit of an S-curve going into it, but generally over most of the range, it's going to be diminishing returns, but there's just it's an open question how fast they diminish. Then there was another question about how the information sharing across models works. And so from a econometrics perspective, we sometimes think about something called seemingly unrelated regressions, where there's just correlation in the error. Here, it's actually matrix factorization is sort of more than that. It's you imagine there's a big matrix of, there's users and items, and I'm trying to estimate the mean utility, so that in principle that matrix could have like a different entry for every user and every item. And that would mean it has very high rank. There's no structure to it. And so, if I know how you feel about 1,000 products, that doesn't help me understand how you feel about the next product. That would be like everything's independent. The matrix factorization approach says, well, actually, like most matrices like that can actually be well approximated by something of lower rank. And that's basically a low rank matrix, if you remember your linear algebra, is, it can be represented as the product of 2 matrices. So like the number of people times k factors times the number of items. And that's essentially saying it's equivalent to being well approximated by something where there's a set of latent characteristics of each item. So say there's 60 characteristics of items in the grocery store, and I can approximate every item in the grocery store by a 60-dimensional vector of unobservables. And then every person has a 60-dimensional preference vector, which says how they feel about those. And if there's this big matrix is well approximated by a low rank matrix, then making that type of latent factor representation will give you good predictions. And so that's the insight from the machine learning literature. That's not my insight, but it's a very useful insight. And we're overlaying the standard choice models with that matrix factorization. So instead of having every user item have their own separate independent shock, we're going to say there's structure on it. And organic lettuce is going to have some characteristics that's similar to organic tomatoes. You have a high preference for organic stuff, and that's going to predict that you like both. And so it allows you, even in a very sparse matrix where I buy 3 products and you buy 3 products and somebody else buys 3 products, as long as there's overlap in that matrix, I'm able to find the structure and make good predictions.
Eric, I think there was a few more questions in the chat for you, if there was any that you wanted to take a look at.
So I guess I'm not looking in the right place.
It's the Q&A, not the chat.
Yeah, I'm sorry, the Q&A.
Let me take one more while he's while he's reading them and choosing the best one. So somebody did ask if I was assuming the prices to be exogenous. I'm not actually assuming the prices to be exogenous. I'm assuming them to be exogenous conditional on stuff, and in particular, conditional on week effects and day of week effects. So and that's basically the placebo analysis was trying to show that conditional on those things that we controlled for, the day, whether you came in on Tuesday or Wednesday of a particular week is exogenous. And so, but whether or not that's true, we try to assess with supplementary analysis. There are potentially fancier ways to do this. And you could also think of it as a regression discontinuity design. If they change the price at noon on Tuesday, then I could compare the people who came in at 11 o'clock to the people who came in at 1 o'clock. But it's at midnight and nobody's coming in at midnight, or not a lot of people. So we kind of think of it as a regression discontinuity between Tuesday and Wednesday. So one other way to think about it is that we have, a whole bunch of weeks in our sample, and and every week there's a bunch of experiments where you randomize whether people showed up on Tuesday or Wednesday, and then we're averaging the results and pooling the results of all of those separate experiments. That's kind of a heuristic for how we're thinking about this. In the Indian data, actually, they change prices at different times. And so there we use a little bit more of the regression discontinuity idea.
Thank you.
So I see the question. Now let me take the first one I see there, which is, does digital commerce investment in terms of time spent to engage, is that considered? And that's interesting because I've been doing a parallel set of work looking at time use. When you think about it, we spend multiple different currencies. We spend dollars when we buy things, and we spend time. We all have finite amounts of time, and choosing to spend on one thing versus the other has an opportunity cost. So you can use that to infer how much people value different things based on how they spend their time. Pete Klenow and Austin Goolsby did some great work doing this, and we've extended that some work with Juhi Oh to get some estimates. And you can compare, for instance, the time people spend on television versus Facebook versus other things. The short answer is that people spend a lot more time on TV still than the internet on average in America, maybe not this group. But the change in time hasn't been very much. In fact, it's been falling, whereas with internet, it's been growing quite a bit, especially mobile internet. So that the implied contribution to well-being is much greater for digital goods and for internet goods, even if the level is not there. But there's a number of assumptions you have to make about how people spend the time. Interestingly, as Goolsby and Klenow noted, people who have a higher opportunity cost of time, higher income or other metrics, will tend to spend less time on free goods. And that sort of gives you an implied demand curve for what their valuations are. But I think ultimately a more comprehensive way of looking at these different currencies that we spend can be really useful to understanding the total valuation. There's a lot of other unpaid and free goods as well. I could quickly touch on the second question there about platforms using, like Facebook, using this pricing mechanism. In fact, they are. Some of you may have seen experiments on Facebook where they've begun using the exact examples that I showed you, offering to pay people to stop using Facebook. Some people are included in it, and they're trying to get an assessment of what consumer valuations are. And we've been talking to them a bit, advising them a little bit on, for no pay, on how they could look at multiple different stakeholders. So their advertisers obviously get value, users get value. Facebook gets value. And then maybe perhaps more subtly, the people who see the ads can get value by having them better targeted and finding out about products that are a better fit for them, a shirt that is more appropriate, or shoes, or whatever. And so the ambitious goal is to measure each of the values that those different groups get, and get a sense of how you, when you tweak, say, the ad load or the level of targeting, you may increase some values and decrease others, and how can you optimize that?
Eric, it would be pretty neat to look and see if you could measure the value of, say, like Facebook or Twitter, and then you could also ask the question of like this counterfactual Twitter or Facebook without ads. So,
Yeah.
so you can kind of lean into it, the business model that you might.
Well, yeah.
propose.
So yeah, that's precisely what we're talking about. Is well, varying the ad load. So think of a matrix with different levels of ad load, different levels of targeting, and then how much disutility people perceive from these different combinations. And of course, they would like to be able to maximize the revenue while minimizing the disutility that people perceive. And one extreme point on that is, that zero ads, and then I guess you have questions about what the revenue model may be. There are externalities and network effects that are part of the story. And conceivably, for some goods, probably not Facebook, you can have a paid model like they do with YouTube.
Great. Well, thank you for a wonderful session. I think that gives us a lot to think about. So let me just make one remark. So the next parallel session is going to be at 3 p.m. Eastern time, and that's in 30 minutes. So if the parallel presenters could join your session now at the start of the break, so we can check your equipment and make sure everything is fine. And then the actual attendees, if you could show up to your room just a few minutes beforehand. And if you need help finding a room, we have virtual attendants who can point you in the right direction. So thank you all very much, and look forward to the next set of parallel sessions.
Thank you, John, and thank you to the code organizers and all the participants with their thoughtful questions.
Thanks from me too.